you, Julie. So, yeah, it's been really fun from my perspective too, working with Julie over the years and getting her insights. So it's only appropriate that the first slide of my talk is one of her photos, and that's not how. I mean, I put this in here well before I knew Julie was going to introduce me, but such has been our interaction. I just like this picture because it shows the complexity of the North State landscape and also the complexity of fire pattern on that landscape. So what I'm going to do today is, first part of the talk is going to be looking at fire trends in California through time, both historical and more recent. And then I'm going to talk about how changes in the fire frequency and intensity have influenced plant populations. And I'm going to focus on 3 chapters, 3 examples. Mountain Lady Slipper, Black Oak, and knobcone pine. I don't know, there's so many talks on knobcone pine, maybe I would have chosen another one, but it's a fascinating species. And then I'm going to finish with some thoughts on the future. And I promise this isn't a doom and gloom talk. It's about change, but not all change is bad. So to start out, I'm going to talk a lot about fire regimes. And so I thought, just so we're on the same page, that I would introduce the concept. It's defined as the frequency, intensity, and pattern of wildfires that prevail in an area. And by pattern, I mean things like the average size of fires, the complexity of those fires, the season of fires. So basically everything about fire in that landscape is a fire regime. So let's start out with some trends over the last 40 years. This is in California. The first one is the number of fires since 1979. And it might surprise some people that the trend has been actually down. And with a fire in the news, you might think otherwise. But John Keeley did a study about a year ago where he looked at the patterns, the causes behind these patterns. And one of the things that has happened over time is that fewer people are smoking. So the incidence of smoking fires has gone down. There's fewer vehicle fires now. There's fewer arson fires. The one source of fire that has been going up is power line fires. But there's not many of those, and so the others overwhelm it. I should mention that 90% of the fires in California are human-caused. But a lot of the human-caused fires, they're near population centers. If you go up into the national forests, where I do most of my work, it's about 50-50 lightning to human-caused. But what's interesting is that while the number of fires has gone down over time, the acres burned has gone up, and quite dramatically, from about 200,000 acres a year in 1979 to about 800,000 acres a year now. So about a 4-fold increase in the amount of fire. And so to understand, why this is going up, we need a little longer term view, and to that I'm going to go to the tree ring record. So this is a fire history study, and I'll explain how to interpret this. But this particular study came from the Shasta Trinity National Forest west of Trinity Lake. And the way you interpret this is every one of these horizontal lines is a cross-section through a stump. Take it with a chainsaw. Every vertical line is a fire registered by that stump. You can see the fires here where the cambium was killed by fire and it grew over, and we can determine the year of the fire. So then if you take a number of these samples, you have a composite fire return interval. And you'll see right away, there's just some distinct periods in this fire history. Prior to 1850, at this site, fire occurred every 3 years on average. And then in 1850, things shifted. It went to every 12 years. And in 1897 was the last fire at this particular site. So what's interesting is that when you look at the pattern of fire here, you'd notice that these fires appeared to be very patchy. Very few of the trees actually registered a fire. And so we believe that at this time, the fire regime was called fuel limited. So anytime the fuels built up enough to carry fire, they would burn. And then an interesting thing happened is when we lengthened the interval between fires just a bit, to 12 years, now all of a sudden fuels become more continuous on the landscape, and all of a sudden every tree in the study is registering the fires. So it's a major shift in the fire regime. And I think both of these shifts you can point to a human cause too. What I'm going to do now is overlay the indigenous population size during this time. It's estimated that some 310,000 or so indigenous peoples lived in this landscape. And then there was some, the mission period started in 1769, brought disease, smallpox and malaria came in the 1830s. You had a big population decline. By the time of the gold rush, there was about half the number of indigenous population. And then with all the miners coming in, it was followed by cultural genocide, and the population really crashed. So it really, it coincides with this shift. And then obviously, fire suppression policies for the latter one. So, one major point I wanted to make with this is that the fire regime already was radically altered prior to active fire suppression. And we always, when we hear in the news about the fire problems in the state, we frequently hear about fire suppression as being the cause. But it's a lot more than we started putting out fire. We also stopped using fire to our benefit or to any large extent. So historically, fire was a combination of lightning ignitions and indigenous burning. I believe that to be the case. For the tribes, the fire use aided travel. It opened up avenues for hunting. It improved the qualities of culturally important plants. And sometimes we hear in the literature that we had historically a lightning regime that was supplemented by indigenous burning, but I think it's also quite possible that in some areas where there was a lot of tribal influence, that it was an indigenous burning regime augmented by lightning. And so this is something that has really shifted in my career, in my own feeling on this, because I grew up in the school of thought that the influence of tribal burning was very localized. And the more I looked at fire history studies, and the more I started to understand how fire moves across the landscape, the less that made sense. And so I really feel like now that the indigenous influence on the burning regime and the pattern of our vegetation, it's really underappreciated how much that was controlled by humans. So regardless of what you believe the source of ignition was, we know from the tree ring record that fire was very frequent in many, at least these forested ecosystems. And one thing to keep in mind is that a lot of the things that we still value today, like old growth forests, like these magnificent oak woodlands, floral diversity, a lot of them were the product of, or at least heavily influenced by, this regime of very frequent, predominantly low severity fire. Right? I say predominantly low because there was a whole mix of different fire types out there. So let's go back to this graph now of area burned by year in California. And you can see that 2018 was the biggest year on recent history. with somewhere like 1.8 million acres burned. But a study that was done by Scott Stevens at Berkeley in 2007, he estimated that historically something like 4.5 to 12 million acres per year burned. So this would be the lower limit of that. And so it puts it in perspective of what used to burn in this landscape. And you think, well, how's that possible after what we went through? But I think a lot of it has to do with the type of fire. It was a very different type of fire back then. So how did a fire shape historical forests? Well, these are some pictures from Wieslander in 1931. A lot of these old pictures, they show a forest, big trees. Here you can see the blackened fire scar evidence on them. It shows an incredible amount of heterogeneity. There were dense patches, there were open areas, light fuels on the forest floor, but there were also dense areas. The early foresters just didn't take pictures of the dense areas, they take the pictures of areas where you could look through. But still, there was a lot of, this is typically how forests looked like, and they were fairly open, and a lot of the early foresters, they viewed this as a negative. And so there's this quote by John Liebberg from 1902. He wrote that suppression of young growth has always been one of the most serious results of fires in this region. The land does not carry more than 35% of the quantity of timber it's capable of supporting. So it became one of the reasons for fire suppression, is the feeling like that if we keep fire out of these forests, we could grow a lot more wood. So then forests started to change. Early in my career at the Forest Service, I lucked into some old historic maps showing what forests looked like in the old growth condition. And this is something I believe I gave a talk on here quite a few years ago on these plots. But this is just 1 acre of one of these plots of old growth Sierra Nevada conifer. It's on a place called the Stanislaw-Tuolumne Experimental Forest. This is an area that historically burned every 6 years, and it hasn't burned since 1889. So old growth, you see these groups of trees of different age classes, widely spaced big trees, gaps, all in an acre. Very diverse. Cross-section. That same acre looked like this in 2008. Like much of the Sierra, it was logged shortly after the plots were mapped, and the logging that time, they took the big trees. But today, it has 2.5 times more trees today than it did in the old growth condition. And you can see, it's just a lot more homogeneous forest than what used to exist. So this has been ongoing through a lot of our landscapes. And this has had consequences to plants. This is paired photograph from a photo point in those same plots. This is a picture of the forest in 1929, pre-logging, and that same photo point today. And notice what's going on the forest floor. We took some data, well, from the old plots, we know that 29% of the forest had shrub cover back then. 2% today. And here you can see in the foreground, almost nothing. My colleague Frank Lake is standing on the stump of that tree right there. So you don't really know the extent of these changes unless you have the good fortune of having old photographs or old plots to show you these changes, because they happen slowly. And there was a recognition even at that time that there might be some fuels consequences to what we were doing. And this is a quote, this is a picture from the National Archives showing accumulation of litter and debris, in 1935. And here's a quote from a forest supervisor in 1930. 21 years of protection has in many places filled up the holes in the forest, and many of you old-timers know of comparatively large areas of almost impenetrable pole stands that were open forests then. This is, of course, as it should be, and we must be prepared to cope with the increased hazard. So, 1930. Foreshadowing. So, that brings us today, and I think there's definitely some fuels consequences to putting out all the fires, and that's pretty apparent. I really feel like the average intensity of fire and severity of those fires, resulting severity, has changed since that time. I mean, it really boils down to physics. If you have frequent fire, you have less fuel consumed. If you have less frequent fire, you have more fuel consumed. And some of this is the fire behavior triangle. Fuels is the top of that fire behavior triangle because it controls everything. It's only when there's enough fuel that topography and weather come into play. So I believe over time, if you look at the change over time, topography obviously doesn't change, so it's really the change in fuels and weather that are driving this. And so I view these change due to obviously the greater amount, and just as importantly, the continuity of fuels over the landscape, the loss of indigenous burning and fire suppression, and I'll go over some indirect effects of that in the next slide, and also climate. But here's just to illustrate the fuels issue. This upper picture is from a prescribed fire in a 9-year-old fuel bed, and this is the typical flame length you see in 9-year-old fuels, 9 years after the last fire. This is the rim fire in long unburned fuels. And obviously, there's confounding here. This was under benign fall conditions of the prescribed fire. This was hot and dry summer conditions. But if the rim fire had been burning in this fuel bed, you would have not seen that fire behavior. So here's an interesting result of fire suppression. I just recently published a paper where we compiled the fire records from the Forest Service for lands in northern and central California, and this is the total acres burned in different fire size categories in both 1911 to 1924 and 2012 or 2002 to 2015. And you can see that in the earlier period, there was quite a few of the acres that were burning occurred in these sort of intermediate-sized fires, and there was very few acres burning in these larger fires, over 30,000 acres. Like the largest fire in this data set was 37,000 acres during that time period, which puts the Mendocino complex in perspective, over 400,000. But then this obviously completely shifted. Most of our acres are burning in these huge fires. And we've essentially taken these smaller fires out of the picture. And these are the small fires that were probably burning under more benign conditions. And we put them out because they're easy to put out. But those are the ones that would have a lesser effect on plants. So if you think of, this is kind of adapted from a graph by Martin and Sapsis. If you think of the severity of fire, the effects of fire from low, moderate, and high, and the proportion of area in these different categories, and then this would be the fire regime without human influence normalized to a straight line. What we've essentially done is we have augmented the number of acres burning at high severity because of fire suppression, because of pushing the fire regime towards these more intense fires and removing this kind of fire from our systems. And it's not that we don't have some low and moderate severity fire burning in these fires. So even in a big campaign fire, some of the acres burn at night or under more benign conditions towards the end of the fire. But on the other hand, with indigenous burning, they likely did a lot of their burning on the shoulder seasons at times where you would expect a low severity effect. So what plants experienced back then to what plants experience now is different. And then climate. It's obviously big on the news these days. This is the mean temperature from 1900 on in the Sierra. Obviously, we're on an upward trend. And climate can influence fire in a lot of direct and indirect ways. It's quite complicated. I'm not going to get deeply into this. But some of the things, the ways that it has influenced fire is through reduced snowpack, longer fire seasons, that allows, besides the direct effect of increased heating on the fuels, you have greater fuel aridity because you have longer, drier periods. With that greater fuel aridity, there's also vegetation stress and mortality and more dead fuel. So a lot of factors come into play. But one thing I want you to keep in mind is that the excess fuels that we've put on this landscape have greatly exacerbated the influence of climate on the fire regime. Is you don't have, if you have light fuels, the consequence of a hot, dry day are much less. So it's because we have all these fuels there, and now that climate's making those fuels volatile, that these two factors are working together to create the issues we have. And I think it's important to remember that those two factors work together. They don't work individually. So now the fun part. This is a botany conference, so let's talk about plants. We're going to talk about how this shift towards relatively infrequent but more severe fire has potentially will influence plants in the future. So first species I want to talk about is Cypripedium montana, mountain lady slipper. This is a species that tends to grow in these small isolated populations in mixed conifer forest, mainly north-facing aspects. It's a CNPS rare plant, limited distribution, moderately threatened, U.S. Forest Service sensitive. Interesting, when looking at the conservation assessment for the species, the perceived threats to the species were, among them, were catastrophic fire, fire suppression or exclusion, prescribed burning in the spring, or prescribed burning in general. So everything about fire. How can that possibly be? No fire or catastrophic fire, everything. So it's obvious that we don't know everything about the fire ecology of this plant. And shortly after I started with the Forest Service, Linnea Hansen invited me out on a field trip looking at related clustered lady slipper on the Plumas National Forest. And this field trip spawned two studies, one Matt Brown's thesis on clustered lady slipper. It also, a little study that we did on the Modoc National Forest looking at the season of prescribed fire on this particular species. So this is a study that was led by Becky Estes, who was a postdoc with me at the time. And we believe from the literature and just looking at the plant, we dug around on these plants and noticed that they have a pretty sensitive looking, buds, 1 or 2 inches down below the ground. We thought they could be sensitive to fire. Also, the literature seemed to suggest that. But without fire, forest densification may be negatively affecting their habitat. So we did a little fire history study with Carl Skinner. And here's Matt Brown holding a cross-section of a burnt incense cedar. And we found that from these cross-sections that in this area that used to experience fire every 4.5 to 8 years, last fire in 1864. So a long time. But if this plant is sensitive to fire, either it came in after the last fire here, or something has fundamentally changed about the way fire now burns. So we did a little study where we took small bites and just put in a few plots in this bigger population because we want to impact that population too much. But what we did is we burned, the idea was to burn some of them in the spring, some of them in the fall. They actually ended up June 29th and September 16th, so really early summer and really late summer actually. But the duct moisture was 22% in the spring burn. I'm going to call it spring, even though it's not spring. 60% in the fall burn. And so there was, and as a result, the amount of duff consumed was a lot more in this spring burn than in the fall burn. And so we followed the stems over time. The burns were done in 2010. And you can see that the fall burns, essentially, they might have had a short little dip, but essentially the population recovered. There wasn't really much detectable effect of the fall burn. Spring burn, we killed some plants. And there's a thought that some of these orchids may go dormant for a while and come up, so we followed them for a time, and they didn't come back. So I think one of the things this study did solidify to us is, yes, indeed, this is a plant that is sensitive to fire. But I don't think you can assume from these data that you're safe with fall burning. I think this has pretty much everything to do with the fact that the spring burn consumed more fuel. Because in the spring, the plants where we didn't consume much fuel, there's a lot of variation. The plants that consumed the least fuel, the plants were fine in the spring. So I think it's about fuel consumption. Anytime you consume a lot of fuel over the top of this plant, it's going to be in trouble. And unfortunately, there's a lot of fuel out there. So, so we have a plant that's not particularly well adapted to fire. And historically, I think Cypripedium likely avoided the direct negative effects of fire because there was so much fire. And this might seem counterintuitive, but when you think about fire, if you have a lot of fire, the effects of that fire are a lot less. There's a lot less fuel builds up, and then when it burns, the amount of heat that's punched into the soil and that might kill this underground bud is much less. So I think with the outlook, with this altered fire regime, is not good. I mean, look at this situation right here. We got fuel like crazy. We have the ingrowth has come in the absence of fire. If this were to burn in a wildfire, it would be toast. So we have a real conundrum with management is, do we burn or thin and potentially or likely kill some plants? Or do we flag and void knowing the next wildfire might kill them all? So neither of these are really happy choices. But I think the best we can do now is to do some fuel manipulation. I really feel like it's the fuel situation, pulling duff and litter and wood away from the base of these plants, and then burn it like crazy. Prescribe burn, make it a priority to lower the fuels in this area. Otherwise, I think these plants are at risk. And this is not just Cypripedium. I think there's a lot of rare plants that are suffering the same fate in the long-term absence of fire. So next, I'll go to Quercus pelagii, California black oak. This is one of our most widespread oaks. It's my second favorite tree after sugar pine. It's just a gorgeous tree when you get into one of these beautiful black oak woodlands. It grows a pretty wide range from the foothill woodlands up to coniferous forests. The tribes really valued the acorns, and they're a keystone species for wildlife. There's a lot of deer, bear, birds, small mammals depend on the acorns. So it has some fire adaptations. For one, it is a resprouting species, so it can come back after high severity fire. And that the leaf litter of black oak, it forms this sort of crunchy fuel bed underneath the tree that with fire, it has a nice flashy fire underneath it, so it's really good for eliminating its competitors at the seedling stage. And in the long-term absence of fire, it is in decline. So it's just a couple pictures I took from the Smoky Creek Research Natural Area on Shasta Trinity National Forest. Oftentimes in the black oaks you see in the forest today, you see all this ingrowth, in this case Douglas fir and black oak, overtopped. It's not a very tall tree, so it's easily overtopped, shaded out, and it eventually dies off. I noted with tremendous irony this sign nailed to this huge black oak right here, prevent forest fires. Meanwhile, this Douglas fir, piercing the crown of the tree will overtop it and eventually kill it, just because we kept the fire out of the system. So for this example, I'm going to stay more local. This is just up the hill here, up the Cohasset Ridge in the Ishi Wilderness on the Alaska National Forest, from a place called Devil's Den. I don't know if any of you have been up there on the Cohasset Ridge, and you can look out and see the Ishi Wilderness. But if you look out there, Deer Creek goes through here, and there's some of these flat plateaus, and they're called pineries, the Graham Pinery and the Beaver Creek Pinery. So the Beaver Creek Pinery is a place that we use as a reference stand for old growth Ponderosa pine black oak forest that has experienced frequent fire and has a fire created spatial pattern. And you can see some of that pattern in these pictures, just an incredibly diverse mixture. Some areas are dominated by black oak, others by Ponderosa pine, and you have just a lot of different structures and heterogeneity. It's a beautiful forest, unfortunately very difficult to get to. Alan Taylor did a fire history up here, and he found that this site, the median fire return interval for any fire was about every 2 years, and for more widespread fires about every 5 years. So this place burned a lot. And most frequent fire 1850, and then like the previous fire history I showed you, the fire returns interval significantly lengthened thereafter. But unlike the other areas, fire continued into the 20th century. We had 4 fires in the 20th century, 1901, 1924, 1990, and 1994. So we thought it would be, we went up there, our agency, this is before I was part of PSW, but they went up there in 1998, put in a bunch of plots to look at this area. And then we remeasured those plots with Alan Taylor, Michelle Copoletta, and Natalie Polakowski back in 2016. But we thought it'd be interesting to look at the Ponderosa black oak dynamics, because this is an area where we know that black oak, or we felt like black oak needs frequent fire. And it's an area that had seen a lot of relatively frequent fire. We were wondering if that might have changed the outcome for black oak. So on the left there, you see a graph showing the trees per acre for seedlings, small saplings, and these are all different size saplings, small trees and large trees for both Ponderosa pine in yellow and black oak in blue. And then when we went back in 2016, things had changed. And when I looked at the Ponderosa pine to black oak ratio, it was 8-to-1 for the large trees, 18-per-1 for the small trees, 26-per-1 for the saplings, and 46-to-1 for the seedlings. And you can see this is Carl Skinner here standing in a sea of Ponderosa pine with his dead black oak stem here. And over this time period, the basal area of Ponderosa pine increased 35%. Black oak essentially stayed the same. And so this was a little bit of a surprise to me. I thought black oak would do better in this situation, but it was really an eye-opener because it gave me the perspective of how completely dependent black oak is on fire and frequent fire. And I feel like when you look at what's happened here, this is talking 22 years without fire. That's just far too long for black oak. A lot of these trees are now getting more fire resistant, and you see some black oak seedlings in here, but they're going to be overtopped and taken over. It needs much more frequent fire to do well. So what's the outlook with the altered regime of less frequent but higher intensity fires? Well, this is one example, a picture from the rim fire, and you can see the winter. But it's hard to get too excited when you got a huge black oak tree like this, top killed by fire. But the outcome over time is that the high severity fire will favor black oak. And but my fear is, when you look at these big trees like that, will we ever grow big trees of that size again with a regime of more intense and less frequent fire? And I'm afraid in a lot of areas it might not be the case. We might end up being replaced by a multi-stemmed shrubbier form of black oak. And you can see some of that ongoing at the other pinery in that previous slide in the Ishi Wilderness. It's the Graham Pinery. This pinery experienced a fire in 1990 that burned pretty hot. It burned hotter here than it did in the Beaver Creek Pinery across the creek. And then it burned again in 2014 in another Campbell fire. But when you look at this vegetation, one thing you note is there's not a whole lot of pine in there. So the fires have taken pine out, so we're going to call it the Graham Oakery now. But you see the challenge is that this is a clump of trees that was killed in 1990, and now it's come back, and this particular clump was killed in 1990 and then again in 2014. So it's just repeated higher intensity fire. It's it'll be black oak, but it will look different than the magnificent black oak forest that we used to have. So my third example is knob cone, and we really learned a lot about knob cone from the talks earlier today. So I'm not going to go into much depth, but it's a thin-barked tree, and it's very sensitive to fire. But it has these serotinous cones that open in the heat of a fire, and so it's really well adapted to this fire regime of less frequent but more intense fire. And at the high end of years between fires, it has an immaturity risk. If you have fire before the trees produce many cones, you can push it out of the system. And then on the other side, a senescence risk. If you go too long without fire, it's a pretty short-lived tree. More than 75 years, the tree declines, and you have a risk of decline of the population. But in this, at least in our area by Redding, where I live, it's not a completely serotinous tree. When some of the branches die, the cones open up, and sometimes the heat of Redding just opens the cones, I think. It's too much. But it does best in this intermediate range here. And so for this slide, I'm going to borrow some figures from Matthew Riley's recent paper in Fremontia, where we saw this earlier today too, but overlapping the distribution of knobcone pine with recent fires, and you can see there's quite a bit of overlap. And so what he did is he looked at the percentage of the range of knobcone that was burned between 1950 and 1984, and less than 5% of the range burned during that time period. So there was a concern at that time that these populations were actually senescing with too little fire. But that turned around. 1984 to 2015, 40% of the range burned, and then in 2018, fully 13% of the range burned. So I think the senescence risk has been substantially reduced here, and the future for knobcone looks bright. So I told you this wasn't going to be a doom and gloom talk. There are going to be winners. And I'll stop with the knobcone slides with this little bit of a paradox. These are a couple of pictures from Whiskeytown National Recreation Area I took a couple of weekends ago. And of course all the stems are black now, but in this picture you'll see that you got knobcone pine that was growing together with black oak. So knobcone, a species that's adapted to high intensity, less frequent fire, co-occurring with black oak, a species best adapted to more frequent, lower intensity fire. So, why are they growing together? And when I first started working in Redding, Jen Gibson, it's too bad she's not here right now, but she invited me out to Whiskeytown on field tours, and we would kick the ground and try to figure out the fire management options in this really weird vegetation association. And I think after the car fire, it's all become a little clearer now. I think that this was likely just a transient vegetation association because we used to have really frequent fire in this landscape. It probably favored black oak. Then we kept fire out for a long time. The black oak persisted because it takes a while for it to be overtopped and shaded out. In the meantime, in the absence of fire, some knobcone came in. Remember, it's not completely serotinous, and it can move into these areas. And so here we had a vegetation type that was just waiting for the next fire to sort things out, and along came the car fire. So my friends up there, they think someday this is going to be the Knobcone National Recreation Area. That's the trajectory this is on. So here we have it's kind of it's daunting and exciting up there because you have basically a blank slate now. And I feel like which direction this vegetation moves, whether it goes towards knobcone or black oak, is in part up to us. If with the status quo, it's probably going to come heavy to knobcone. If we use more frequent fire, pushing more frequent fire, so burning before the knob cones produce many cones, we can eventually move that towards black oak. And I think part of the reason we were initially puzzled here is that we were viewing this vegetation association too statically, as if there was some sort of fire regime that would work for both of these species simultaneously. I think it's pretty clear now that that's not the case, that this is more of a transient type. So, I'm just going to offer some final thoughts. I think one of the main take-home points that I wanted to make with this talk is just how many aspects of our vegetation are shaped by fire, about how important fire is in the system, both the fire and the lack of fire, and how it shaped our vegetation. And the changes that we've seen in our lifetimes are oftentimes quite dynamic. And I think a lot of that stems from, at least this is my theory, that it's because our flora is adapting to this completely different fire regime. So we're in a time of change. And so another thing that I feel like underappreciated is just how frequent fire used to be in this landscape, and also how much the indigenous burning, what role that used to play in shaping our vegetation. At one point, I forgot to make with that knob cone is that you saw on that map is the really scattered distribution of knob cone. Oftentimes, when you have the scattered relative populations, climate refugia are one reason that's given. I think it's entirely possible with the amount of indigenous burning in this landscape and just natural and other fires that happen, that these are the fire refugia. And that, if that's the case, perhaps that distribution of knob cone has a human signature. So just something to consider, and just complete rampant speculation. So the way I view it, going forward, we have three options. We can either we can accept this change to a vegetation that's actually better adapted to this new fire regime, and one of the good news here is that not all species that will benefit are exotic. There's actually some natives that are going to do just fine. Unless you have too much fire, shrubs like Archistophilus, Ceanothus, Serotinous species will probably do quite well. The bad news is that if you lengthen the interval between fires, you have more fuel. And some of these plants that tend to be favored by higher severity fire also tend to burn hot. And so there's a potential for greater impact to human lives and infrastructure when it does burn. Another alternative is to fight against the change, try to maintain species out of balance with this new fire regime. And I think we do this all the time at great inefficiency and cost. But I'm going to assume this is not the path that we want to go moving forward. And so another option is change the fire regime or use more fire, much as our indigenous population in this landscape once did. It's interesting, these days, the fires in Australia are big in the news, and their situation in a lot of ways mirrors our own. They have seasonally hot and dry weather. They have a fire-adapted vegetation. I don't know if any of you caught on NPR, there was an interview of an Australian fire manager a couple weeks ago where he described how the situation in Australia has really increased their interest in indigenous fire management again. And so apparently the Aboriginal peoples, they burned a great deal, and it was an art form. And this art form was largely lost. And as a result, they're also sitting on a pile of accumulated biomass. And now they're in a hot and dry period, and unfortunately experiencing the consequences of that. And that same thing can happen here. So one of the advantages of using more fire then would be it would help buffer against the effects of climatic warming. If you have less fuel, then the effect of climatic warming would be less. And also, with less fuel, fewer impacts to plants, human lives, and infrastructure. And for those of us who like plant diversity, there's some advantages too. With a diverse fire regime, you expect a greater diversity in our flora. But there's no silver bullet. Alas, more smoke. Especially, you expect more smoke, especially initially, as 100 to 150 years of accumulated biomass are consumed by fire. And there's going to be trade-offs to reduce fuels and improve the overall habitat. Some plants might do well. Other rare plants may suffer the consequences, at least initially. So I think oftentimes we have tended to focus on sort of the immediate short-term threats to plant population as a result of management, like prescribed fire or thinning, and pay a lot less attention to the long-term future undefined threats like wildfire. And so I'm wondering, with this increase in trend in fire activity, does that calculus change? Do we need to start accepting greater some amount of greater risk of management actions in order to prevent a future catastrophe? And I'm thinking of plants like Cypripedium, but there's a lot of other plants in that boat. So, another question is, will we ever get back to burning like we once did? I don't think that's likely either. We have 40 million people living in the state. There's so many constraints to burning today, including air quality, risk to infrastructure, and we can't just let all unintentional emissions burn. There's many human-caused fires that happen at the worst possible times, and that will have a negative effect to vegetation. With our climate and population size, I think we're always going to depend on a robust suppression infrastructure. But it's my hope that we at least get to the point where we're able to use our fire management resources more proactively. And the more we can preempt wildfire by burning, like using more prescribed fire or wildfire for resource benefit, I think the better off we'll be. So I'm going to leave you with a photo of the type of fire that is most underrepresented in our landscapes today. It's a prescribed fire in Black Oak on the Shasta Trinity National Forest that I was lucky enough to be involved in. But this is the kind of fire we don't oftentimes see in media reports of fire. Low flames, it's not very scary, and I think this is the type of fire we need a lot more of. So with that, I'll conclude. I just want to say thanks for the invitation to give this talk. It's really an honor to be up here. So thank you.